Hello and welcome to the next lecture of terpenoids. Today we will discuss on very important compound geraniol, its occurrence, structure determination, synthesis, isomerism, oxidation reactions and NMR of geraniol. This geraniol, it is a very important constituent of rose oil. As you can see, it is an acyclic monoterpenoid containing two isoprene units joined head to tail, and a primary alcoholic group is present in geraniol. It is, in addition to rose oil, it is also found in parmosa oil and citranola oil. It also occurs in small quantities in geranium, lemon and many essential oils. That's why it is its utility is in perfumes, lotions, creams, aftershave lotions, detergents and soap. It vaporizes at 230 degrees centigrade. When extracted from rose oil, it is pale yellow in color, but its pure form is colorless. Its uses are as an oxidant, antioxidant, anti-inflammatory, antibacterial, and they are used as antifungals. Next we come to the structure determination of geraniol. It's a chemical method. Earlier scientists used to, there were no sophisticated methods at that time, so they used to rely on the chemical methods. So based on the empirical formula and elemental analysis, its molecular formula was determined as C10H18O, which gives very important information about the structure of geraniol. C10 means there are two isoprene units which are joined head to tail, as we assume that they are joined head to tail according to special isoprene rule, and according to the molecular formula it belongs to acyclic monoterpenoid class. And now we determine the nature of unsaturation. It contains as it contains two isoprene units, that means double bond should be present here, and we are using this formula. Using this formula of double bond equivalent x plus y minus y by 2, putting the values of x and y as 10 and 18, we get 2 double bond equivalent. That means there are two double bonds, either two double bonds are present or one ring, or one double bond is present or two rings are present. Now let us see the analysis of unsaturation, or let us see what this type of unsaturation is. It adds on two molecules of hydrogen yielding tetrahydro derivative C10H22O, and on bromination it forms a tetrabromo derivative. On this analysis of these two formula, we can see that C10H22 and here C10H18O. The difference between the hydrogen atoms is of 4 hydrogen atoms, and you can also see the bromine, there are 4 bromine atoms added. This means, and this also it is a saturated compound. This means that two molecules of hydrogen or two molecules of bromine have been added to yield the saturated compound. This means that two double bonds are present in geraniol. Now let us come to the nature of the oxygen atom in geraniol. It reacts with ferric ammonium nitrate and gives red color. This means that all alcoholic group is present. Now we can see how this alcoholic group may be secondary, primary or tertiary. On oxidation, let us see, on oxidation of geraniol, it yields aldehyde which is known as citral. We have already studied the structure of citral. It is an aldehyde, and on further oxidation of this citral yields geranic acid. On reduction, this citral again yields geraniol with sodium amalgam. This means that the group present is the primary alcoholic group. As we come to the synthesis of geraniol, its first synthesis is from citral. On reduction with sodium amalgam, it yields geraniol, yielding the plus small amounts of nerol is also formed. The second synthesis is from linerol. It's a laboratory synthesis. Linerol is also an acyclic monoterpenoid, bearing tertiary alcoholic group. In the presence of acid, it undergoes carbocation rearrangement and ultimately it converts into geraniol. Next we come to another synthesis of geraniol. It is from ethyl acetoacetate and allylic bromide. Allyl bromide on treating with LDA. Ethyl acetoacetate gives enolate ion on treated with LDA, and it then behaves as an oxygen nucleophile. Allyl bromide gives nucleophilic substitution with enolate to give allyl vinyl ether, as you can see here. This allyl vinyl ether, it undergoes Claisen rearrangement. This is a sigma 3+3 sigmatropic rearrangement, and it undergoes rearrangement on heating, producing this ester. Then in this compound there are two functional groups. This ester group and ketonic group. First we have to protect this ketonic group, which is done with the protection is done with ethylene glycol. Here we have protected this group, and then we have undergoes the reactions with the lithium aluminum hydride, yielding the primary alcoholic group, which now there are two steps here. First we treat with acetic anhydride. This primary alcoholic group converts into acer. Protection of this, we have protected this alcoholic group, and second step is the deprotection of this carbonyl group, yielding the carbonyl group again. Here you can see there are 5 and 4 carbon atoms. That means 9 carbon atoms are present. We need one more carbon atom in geraniol because there are C10 carbon atoms. This can be done with the Grignard reagent, methyl magnesium bromide. We have treated, converting it into tertiary alcoholic group, and then we can react it with acetic anhydride. Dehydration takes place here, as you can see. Dehydrated product. This is again an acyclic diene is formed here. Then this diene undergoes scope rearrangement, 3+3 rearrangement, yielding the product, which on KOH hydrolysis we again get the alcoholic group here, which can be rewrite as this. This one is geraniol. This is the synthesis. You can see 5 carbon atoms from allyl bromide, 4 carbon atoms from ethyl acetoacetate, and 1 carbon atom from methyl magnesium bromide. In this way 10 carbon atoms is involved in the synthesis of geraniol. Next we come to geraniol and nerol. Citral on reduction with sodium amalgam yields geraniol and small quantities of nerol. What is this nerol? These two are geometrical isomerism, as you can see here. Only the cis and trans form is involved here. We can assign geraniol has been assigned trans configuration and nerol as the cis configuration on the basis of this reaction of geraniol, or it yields geraniol and nerol with the sulfuric acid. It yields alpha terpeniol. But in case of nerol, this isomerization is 9 times faster than in geraniol. Thus we can say that it is nerol is in cis form and geraniol is in trans form. We can also see the explanation here. As you can see, both geraniol and nerol, they yield tetrahydro derivative on reduction. In the presence of acid, you can see this geraniol, as you can see, cyclization. This is in transformed geraniol, so this during cyclization these are very far away and yields terpeneol, this carbocation, and ultimately terpenylol. This reaction is slower as comparison to nerol. You can see here the formation of carbocation. This is nerol is in cis form, and so they are nearer to each other, and this cyclization takes place very easily or faster because of this cis form. So we can say that the double bond in nerol is assigned as a cis form, while the same double bond in geraniol is assigned the trans form. Oxidation reactions of geraniol. It undergoes especially 3 types of oxidation reaction. First is the allylic oxidation with manganese dioxide, and you can see that this converts into, this primary alcoholic groups converts into alcoholic group etc. Next is the oxidative degradation on treatment with ozone. It converts into, and methyl sulfide, it converts into glyoxal, yielding acetone here, and labyl aldehyde. Vigorous oxidation degradation yields levulinic acid, and further the glycol is converted into oxalic acid and acetone. It also undergoes sharpless asymmetric epoxidation, and yields epoxidation takes place at this double bond, yielding two major product, epoxide and the minor product. Last of all, we come to the NMR spectrum of geraniol. As you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogen atoms, but the peaks we get 1, 2, 3, 4, 5, 6 in proton NMR. 6 peaks because first you can say that these methyl groups are in the same environment, and they we get the peak at 1.67. Given in the same environment, it gives only one peak at 1.67. Here there are two CH2 groups, they are all in the same environment, and we get only one peak here at 2.03. Next there is one here CH2 group 4.13. There are two ethylenic hydrogen atoms, but they are both are in the different environment, so we get two peaks, one at 5.4 because it is a de-shielded hydrogen, whereas this is on the higher peak, P5.01. This is the shielding effect is shown here. Similarly, there is 1.60 also, there is one peak, singlet peak. 4.13 is the CH2 group, it's a doublet. And the C13, similarly C13 in NMR also spectroscopy, we get 10 signals corresponding to these 59.2, 139.1, 16.2, 39.6, 26.5, 123.7, 25.7, 131.6 and 17.7. As I said, there are 10 signals in there, and in proton NMR there are 6 signals. That's all. Thank you.